Hi X203. For this video, we're going to be reviewing the properties of relations. So we've got our set of 1, 2, 3, 4, and a few different relations on that set, and we'd like to see what properties each of these relations have. Just for convenience, I've got our definitions of each of these relation properties written out at the top. So for part A, we've got this set of 1 relates to 1 and 1 relates to 3. So let's see, is this reflexive? Does every element relate to itself? And right away we're going to see that no, we're missing 2 relates to 2, and same with 3, and same with 4. So this is definitely not reflexive. But is it symmetric? For that one, we're going to see, well, if x relates to y, then y should relate back to x. But for this one, I see that 1 relates to 3, but I don't have anything that 3 relates to 1. So this one is not symmetric. Anti-symmetric, we're saying that if 2 different elements relate to each other, then they have to be the same element. And let's see, do 2 elements ever relate to each other? Well, 1 relates to 1, and 1 relates to 1, but we already knew that 1 equals itself, so that's okay. But we don't have any different pairs of elements that relate to each other, so there's really nothing to violate this property. So it is anti-symmetric. And then for transitive, we're going to see, well, if x relates to y and y relates to z, then x should relate to z. And for this one, there's a couple ways we could pick our x, y, and z. We could say, well, 1 relates to 1, and 1 relates to 1, so 1 has to relate to 1. But that's kind of silly. We already knew that. And then for the other options, we could say, well, 1 relates to 1, and 1 relates to 3, so 1 should relate to 3. But again, we already have that. We don't really need to worry about that. So this is a transitive relation. Now let's look at part B. 1 relates to 1, 3 relates to 3, and 4 relates to 4. So I'm noticing right from the start, 2 doesn't relate to 2, so there's no way to make this reflexive. But how about symmetric? If x relates to y, does y relate to x? And since all we've got in this are just elements relating to themselves, this is going to work out to be symmetric. Since again, 1 relates to 1, so 1 should relate to 1. Yeah, we got that. Now for anti-symmetric, somewhat surprisingly, this one also works as well. Same principle as we were talking in part A. 1 relates to 1, and 1 relates to 1, so 1 equals 1. But that's okay. We don't have any different pairs that relate to each other, so again, there's no way that we could violate this anti-symmetry. And then for transitive, well, there's just elements relating to themselves, and we saw in part A how that still worked with transitive. So this is also going to be a transitive relation. Moving on to part C, this one is maybe a little more interesting. We have that 2 relates to 3, and 1 relates to 4, 3 relates to 2, and 4 relates to 1. So is this reflexive? Definitely not. We don't have 1 relates to 1, we don't have 2 relates to 2. In fact, nothing relates to itself. So very much not reflexive. For symmetric, well, we've got 2 relates to 3, but we also have 3 relates to 2, and so that works. And 1 relates to 4 and 4 relates to 1, so that works. So this is a symmetric relation. We're going to see for the first time something that isn't anti-symmetric. Since 2 relates to 3 and 3 relates back to 2, but this time 3 and 2 are different elements, so we cannot have our principle of anti-symmetry. For transitive, this one might be a little tricky, because we're looking for, well, if x relates to y and y relates to z, then x should relate to z. And there's maybe nothing that leaps off the page as breaking that property. But interestingly, one way that we could check this is, well, 2 relates to 3, and 3 relates to 2, so 2 should relate to 2, but I don't have that. So even though x and z are the same element in this case, we still have to check that case, and so this still breaks transitivity. Finally, let's look at part D. This one is a little bit longer than some of our other relations, but we can still use the same techniques. So let's see, is it reflexive? Well, it's missing 1 relates to 1, so no, it can't be reflexive. How about symmetric? Well, 2 relates to 2 and 2 relates to 2, that's fine. 2 relates to 3, and I also see that 3 relates to 2, so that's okay as well. But then 2 relates to 4, and I don't see anywhere that 4 relates to 2. So that's going to break our symmetry. This is not a symmetric relation. It's also not anti-symmetric, since we noticed earlier 2 relates to 3, 3 relates back to 2, but they're not the same element, so this is not anti-symmetric. Now for transitivity. This one we're going to have to be pretty methodical, since there's so many combinations, but we can save ourselves a little bit of work. And the trick here comes with these pairs with the same element, like 2 relates to 2. So if we've got 2 relates to 2, then we know that if we've got 2 relates to 3, then 2 should relate to 3. But that feels pretty circular, since, yeah, if 2 relates to 3 is there, then 2 relates to 3 is there. And for this reason, we can see that the ones where an element relates to itself, those don't really ever break transitivity, and so we don't have to worry as much about those. So let's focus on our other pairs. 2 relates to 3, and let's see, well, 3 relates to 2, so 2 should relate to 2. That works. 2 relates to 3, and 3 relates to 4, so 2 should relate to 4, and we've got that one. Then 3 relates to 2, 2 relates to 3, so 3 should relate to 3. That's good. And then 3 relates to 4, but 4 doesn't relate to anything else, so that's not going to break transitivity either. And so we can see we saved ourselves a bit of work by not having to check everything with 2 relates to 2 or 3 relates to 3, and we could see that this is a transitive relation.